Log is applied to this expression. This expression has to be positive. Can anyone tell me what to write? Anyone? So if you compare these two, what will you say that I should write and solve? Anyone? What did we do with the square root? What did we write for the square root? No, we did not write that equals 0. Yes, x squared minus x minus 2, correct? Without 0. It has a vertical asymptote at 0. The radical is okay with 0, but log is not okay with 0. Very good. So now I know how to solve this from the previous chapter. Yes, I have to factor it. How do I factor x squared minus x minus 2? Very good. Now it's up to you. The method you like, you can apply any method. So this is the method I like to present because I think it's easier and visual, but you may say, I don't like it. I'm using my own, and I'm fine. Use the method you like, the method you understand. X can be any real number. Can anyone tell us what numbers go in here?
-1 and 2.
Very good. Do you all agree with -1 and 2? X plus 1 is 0 when x is -1. X minus 2 is 0 when x is 2. Would you agree? In the row for x minus 2, there must be a 0 somewhere. Where? Under? Good. In the row for x plus 1, there must be a 0 somewhere. But that's how I got those numbers. Right. What happens to the product when x is -1? Perfect. What happens to the product when x is 2? 0. And now remember, these are linear functions with a positive slope. They look like this. They must come from negative values. They cross the x-axis where they are 0, and they will continue forever to positive infinity. So both these two have this sign. Ooh. Good. So on the first subinterval, can anyone give us the sign of this product? Do you all agree with positive? Can anyone give us the sign of the product in the middle? Can anyone give us the sign of the product in the last? Positive. Good. So now this tells me what to choose. X in the interval, or if you want domain, whatever you want to write. Negative infinity to -1 with a parenthesis, because I don't have equal symbol, equal 0, union 2 to infinity. Do you all agree with the domain? So the reason I wanted to talk about this before looking at equations is because I would like you to remember that log is a function with restrictions. It's not a friendly function from that point of view. And whatever solutions you get, and I'm going to write this down in a minute, when you solve a log equation, you either state domain. This is easier for me. I state the domain and I check against the domain. I'll show you in a minute. Or you say, no, I don't want to state the domain. It takes me too long to think about it. But you must check the solutions back in the original problem. So one or the other. You don't have to be consistent. On problem 5, you can check the solution. On problem 6, you can find the domain. I'm fine with that. But you remember, log is a function with restrictions. So note, when solving log equations, choose from 1. You must choose from 1. State domain. And of course, check against the domain. And 2, check solutions. I should say prospect solutions because they may work or may not work. Potential solutions, prospect. So check prospect solutions back in the original problem equation. So when solving log equations, you must choose one or the other. The first one is state the domain, and when you get whatever, you just say, is it in the domain? Yeah, it's a solution. It's not in the domain. It's not a solution. Or the second option is you must, at the very end, you get one solution, two solutions, whatever you get, prospect solutions, you have to go back and check them in the original problem. I prefer this. This is easier for me because sometimes I forget to check at the end. And that will mess me up, especially if the solution is not the solution, right? Yes?
So your number one is just doing your chart thing and then
No,
okay.
no, I'll show you in a minute. So the chart is only when I have to study the sign of a product or a ratio. When I solve log equations, I will not have to do that. I discussed this just to show you that how I state the domain, how I find the domain.
Right, okay.
Oh, that's what you were asking.
Okay, right. So the chart will get us to the domain.
To domain,
Yes,
exactly.
okay.
However, this was a much more complicated situation. I would not have this in equations. Okay, so equations will have logs with a linear quantity, not a quadratic that I have to factor and da 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 da. Okay, so your book does not show anything beyond that. So let's start with the first example. Yes, please.
So you said natural logs and logs are the same thing, right?
No, log is base 10, ln is base e. They are totally different. Their shape is similar.
What about the restrictions?
All the restrictions are all the same for any log, any base. So if it's log base 1700 of x, x must be greater than 0. Right. Okay, back to page 490. I would like to start with, let's say, 53. 490. So that is log base 3 of x plus 5 equals 3. I'm sorry, I copied incorrectly. Log base 4. Log base 4 of x plus 5. If you like to state the domain, which I highly recommend because you will have a problem in which you will have to determine the domain in the log. Okay, then it's very simple. What will you tell me to write? Exactly. So then x is greater than negative 5. So if my solution will be greater than negative 5, I'll accept it. If it's not greater than negative 5, I will say no way. And now I know that this is a log equation, and it can be easily converted into an exponential one. Remember, this is the most important concept in this chapter. To be able to learn to change a log equation to an exponential and an exponential into a log. So can anyone give us the exponential? 4 power of 3 equals x plus 5. Okay, so 64 minus 5 equals x, so x equals 61. Done. Is 61 greater than negative 5? So it means that it will be accepted. Oh, what did I write 61? Okay, it's 59, I'm sorry. Sorry about that. 64 minus 5 is not 61. I was subtracting 3 in my head. Okay, now let's move on to something a little bit more involved, like 67. Same page. Log base 5 of x plus log base 5 of 4x minus 1 equals 1. Now this is a sum of two logs. Both logs, I cannot change anything before, if you decide to state the domain, I cannot change anything before I find the domain. What is the domain of this function here, this one? What do I have to write for this one? Of course. Forget about this one now. What do I have to write for this one? Good. So this is greater than 0, and this is greater than Move 1, divide by 4, 1/4. So now imagine 0 to infinity intersected with 1/4 to infinity. I need the intersection because I need both to exist at the same time. So x must be definitely greater than. Okay, let's look at this. Of course, but let me show it because not everyone said that yet. So this is 0 to infinity, and this is 1/4 to infinity. We need both red and green at the same time. So what is the common territory of these two? Okay, so if the solution is not greater than 1/4, it cannot be accepted. Is that okay? Good. So now we learn how to condense this. That's why we learn to condense for the equations. Can anyone tell us what to write instead of this? I want one log.
Log base 5. And you put x parentheses.
Very good. It's the product. Very good. And now I want to convert it. Excellent. Indeed. Log plus log changes into log of the product. Excellent. So then I want to convert this into an exponential equation. Ready? Yes? Yes. X times 4x minus 1. From the base. The base raised to power 1 equals x times 4x plus 1. What would you do now? I can never divide in a quadratic equation by anything.
Give 5.
Yes. So I have to distribute 4x squared minus x plus, minus 5 equals 0. Right? 4x squared minus x minus 5 equals 0. What now? In a quadratic equation, I have to have everything set to equal to 0. I can factor by grouping, by writing 4x squared minus 5x plus 4x minus 5 equals 0. How do I know that? Remember, the product is negative 20, and the sum is negative 1. So that must be negative 5 and 4. And now it will be factoring by grouping. What will you factor out from the first two?
X.
Good. What is left in parentheses?
4x minus 1.
Very good. What should be left from the other two? Otherwise, I can continue. 4x minus 5. And now I look. Sign and factor.
Plus 1.
Plus 1. Good. So then now I factor out what? Very good. And what is left in parentheses?
X plus 1.
Very good. So as expected, we have two solutions, two options. And what are they?
5/4
Very good. 5/4 and negative 1. Not so fast. We worked hard to determine the domain. It says if it's not greater than 1/4, you must discard it. So do we discard anything or keep both?
Discard the other one.
I think it's more difficult to go back and check than state the domain, but it's up to you. Both methods are acceptable. Any questions?
Is there any possibility that both solutions
Yes.
cannot be?
Yes, absolutely. Yes. Okay, let's look at 79. 79 log 3x minus 3 equals log x plus 1 plus log 4. We have two logs in here. How do I find the domain of the first one? What do I have to write?
3x minus 3 is 0.
Greater than 0. And the other one?
X plus 1 is greater than 0.
Excellent. So So from here, I know that x is greater than 1. And from here, x is greater than -1. Imagine from -1 to infinity, and then imagine from 1 to infinity. Where is the common territory? Very good. Do you all see greater than 1? Please say no. If you don't, it's okay, and I'll show it. Do we see that? One more time. From -1 to infinity, and then from 1 to infinity. They overlap only between 1 and infinity. We agree? Okay. So if the solution is not greater than 1, I have to say no way. Good. The left-hand side is the left-hand side. You can condense the right. You can bring x to, you can bring this one to the other side. It doesn't matter. You can condense the way it is. It's up to you. So if I condense the way it is, the left-hand side is condensed. What would you do to the right-hand side? 4 times x plus 1. Okay, now please pay attention. Exactly the same concept that we used in exponentials. Two numbers are equal. Their logs are equal. Can this one be 15 and this one 9? No. One more time. Two numbers are equal. Their logs are the same. What should happen to these numbers? They must be the same. Otherwise, the log of this will never equal the log of that, because we know it's one-to-one function. I can't have here 5 and here 15. Good. So therefore, this is much easier. I don't have to change it into an exponential. I only have to say this. And this is a linear equation. And I will move 4x to the left. And I will move -3 to the right. So 4x on this side will make a -x, and 3 on this side will make a 7. So then x equals -7. And that's my solution. And I will say not so fast. For me, it's more cumbersome to go back and check. For me. So now what? What do you conclude about equation from 79? So then the solution is no solutions. Very good. Okay. We will come back to more equations. I would like to just show you more problems. They're all the same. I would say that they are quite simple. Okay. But we have to understand the mechanism. So the mechanism will take a little bit of time, but once we understand the mechanism, you'll see that all these word problems in this chapter are interesting, in my opinion, and not difficult. Okay. This is the last section of chapter 4, applications. There are 3 major groups in which we use exponential functions, and there are other groups for logarithmic functions, but in this section I would like to discuss 3 of them. One is called exponential growth. The other one is called exponential decay. And the last one is called logistic function. I should say logistic functions. There are so many. We are not going to memorize anything about the logistic function. The logistic function will be given to us. The other 2 are extremely similar. The notation is different because they have different meanings. Okay, let me explain the difference between these 2. Exponential growth. It's a function that shows exponential growth. It's the fastest possible growth. Populations grow exponentially. Rabbits, rats grow exponentially. Bacteria grow exponentially. So when we talk about these, population, bacteria, number of, we use this notation, A of t, the amount or the number function of t. when we talk about exponential decay, we're talking about mass. So we don't want that, but assuming we have here 100 milligrams of a radioactive substance, that radioactive substance decreases its mass in time using an exponential decay. So it's not this, but it's this, right? It's an exponential decay. It's a decreasing function. Now, for this one, we use the notation m of t because we're talking about mass of t. So this is number, counting, and this is mass. The two equations will be very similar, but one of them will have a positive power. The other one will have a negative power. So here are the equations. The exponential growth function is a of t, a0, initial number of rats, initial number of people, initial number of mice, rabbits, initial number of bacteria. That's the initial, multiplied by e to kt. T is time. T is the variable in the problem. This is the only variable. K is the growth rate. Now, in the exponential decay, everything is the same. You will recognize it in a blink. Look at this. M of t equals m0 e to negative kt. Of course, this is the initial mass. Of course, k is the decay rate. T is the same. Time is a function of time only. This is a number, this is a number, this is a number. So you see that this is an exponential function because the exponent has the variable, time. K is a number and A0 is a number. This is an exponential decay because the negative power will have 1 over e. And the base will be 1 over e here and base e here. That's why this is increasing on all its domain and this one is decreasing on all its domain. Let's work on that. On page 505, and maybe I should start with the logistic function that is extremely easy to work with. Sometimes solving an equation may be slightly more difficult, but let's see, 37. On page 505. The logistic growth function, you don't have to memorize any of this. You have to remember these two. They will be given to you, however, but I would like you to remember those two. Okay, the logistic growth function is given f of t, which is 100,000, divided by 1 plus 5,000 times e to negative t. As you see, and indeed a sophisticated function. It says it describes the number of people, f of t. So f of t, I take notes, number of people. Okay. F of t who have become ill with influenza, t weeks, t in weeks. Okay. After its initial outbreak in a particular community. How many people became ill with the flu when the epidemic began? What does that mean? How many people became ill when the epidemic began? What am I asked to find? Say it again.
I'm just an amount.
Okay, let's read it again. The logistic growth function given to us describes the number of people. So f of t is number of people who became ill with influenza t weeks after its initial outbreak in a particular community. How many people became ill with the flu when the epidemic began?
So f of 1.
F of 1 is 1 week later.
F of 0.
F of 0. So in part 1, let's find f of 0. Let's do this together. How much is e raised to 0?
1.
Right. How much is 1 times 5,000? 5,000. How much is 5,000 plus 1? Good. So then I have 100,000 divided by 1,001. When I divide by 5,000, I will have 100 divided by 5, which is 20. When I divide by 2001, I have less than 20. And since I cannot say that I have 3.5 cats, I cannot say that I have 19.5 people. So I'm going to say 19 people. Yes.
It's actually 19.9.
Oh, if that's the case, it's 20. Okay, sorry about that. Good.
9968.
19 point. Well, again, I would not say 20 people. Because 19.6 is not right. So that's why I thought that maybe I made a mistake, but I would not say 20 people because I cannot round up. Right? I can round up when it comes to money, I can round up when it comes to time, but I cannot round up number of people. I can't say I have 3.9 people, right? Good. So I would my answer would be 19, not approximately 20. How many people were ill by the end of the 4th week? What am I asked to do now? F of 4. So with the graphing calculator, I will put in 100,000. Since the numerator has only one number, I will not put it in parentheses. And I will divide by 1 plus 5,000 times E. Careful, second and ln. Second and ln. And that is -4, correct? And then close the parenthesis and press enter. I did not put -5.
On the calculator, you said -4. You said -4.
Oh, fine. I looked at 5 and I said 5. No, absolutely, it's 4. Sorry about that. I meant 4. You're right. Okay, again, I cannot say anything else but 1,080. 1,080 people. Question part C. What is the limiting size of the population that becomes ill? When we talk about limiting size of the population, is the maximum possible, which means we start with 19 people who get the flu. 4 weeks later, we have 1,080. 10 weeks later, we have blah. 15 weeks later, we have this. 100 weeks later, we have this. So what am I getting at? What am I really telling you? Yes, the trend going towards what? Towards infinity. Okay, we cannot really say time is infinity, but let's see what happens here. So number 3, as t approaches infinity. Here's one way. Let's go back to y equals this time. Let's put it in y equals, let's put the function, which has 100,000. Divided, do I have 6? Yes. No, I have 1,000,000, don't I? Okay, divided by, I only need 100,000, yes. Divided by 1 plus. I hope not.
No, that's right.
Oh,
So that's okay. I'd rather go back and check. 5,000 times e to -x and close the parenthesis and close the parenthesis again. I like to put parentheses around the numerator. And now let's go to around the power. Now let's go to second and table. So I want to see what happened in the first week. Here it is, 19.999, which is 19 people. I want to see what happens after the 4. Yes, 1,080. I'm going to say what happens after 10 weeks. What happens after 40 weeks? What happens after 50 weeks? What happens after 60 weeks? What is the limiting size potential maximum possible? 100,000. And what is that for this function? What is that for this function? When x approaches infinity, y approaches 100,000. What is this? Horizontal asymptote. Very good. That is a horizontal asymptote. As t approaches infinity, f of t approaches one more time, approaches what? 100,000. Therefore, y equals 100,000 is a horizontal asymptote. Very good. Okay, so this is an example of logistic function. And we'll have more when even today, if possible, or when we review on Wednesday. Now I would like to come back to this is it. That's all we're going to need in this chapter. I need to show you exponential growth, and I need to show you exponential decay. Okay. So let's look at the exponential growth first of all. On page 504. Okay. Let's talk about number 8. 8 on page 504. Okay. In the year 2000, the population of the Palestinians in the West Bank, Gaza Strip, and East Jerusalem was approximately 3.2 million. I'm taking notes as I read. By the year 2050, it is predicted to grow to 12 million. Use the exponential growth model in which t is the number of years. T, number of years since the year 2000. To find the exponential growth function that models the data. When I'm given something like this, and I know it's an exponential growth, I will immediately write my model. A of t equals a0 e to kt. This is the model. T is the x, the variable in the problem. A is the function, f of t, or a of t. What is not known here is a0, which is the initial population, and k, which is the exponential growth rate. So I do not have a0. I do indirectly, but let's say I don't have it right now, and I don't have k. E is a number, t is the variable in the problem, and a is the function, a of t, or f of t. Good. So now I'm told t is the number of years since 2000, which means t equals 0 for 2000. Would you agree?
Yes.
Good. So I am told what happens when t is 0. So a of 0 is, from the given information, I know that a of 0 is exactly. But that is the initial value. That is a0. So when I plug in 0 in the function, a of 0 is a0, because 0 here means this is 1. So I have one piece of the puzzle. So I know that now that a of t equals 3.2 e to kt. So I made one step forward. I found the initial value, which is, or the initial number of people, 3.2 million. Now I'm still missing one piece of the puzzle. Which piece? K. I do not have K. So I used this already. Now it's time for me to look at this. This piece says that when t is 50 excellent years, then a of 50 is 12 million. So this is the information that I have to put in the equation right now. Can anyone tell us how to write that second piece of information? When t is 50, a of 50 is 12. So what do I write for a of t? A of t is how much? No, t is 50. So A of t is 12 equals 3.2 times e to what? 50k. Very good. So one more time. A of 50 is 12. So when t is 50, 3.2 e to 50 times k, or k times 50. Now, this is the equation I have to solve for.
Okay.
Excellent. How do I do that? What is the mandatory first step? I can't, as long as it's a product.
Subtract 12.
I cannot subtract 12. It will not help. Exactly. 12 divided by 3.2 equals e to 50k. Clean it up. Indeed, I have to divide both sides by 3.2. Now I'm ready to do what? I have to apply something that will bring k down, log. So I have to apply natural log to both sides. The left-hand side is natural log of 12 over 3.2. Do not bother with it at all. But can anyone tell us the right-hand side? What will that equal to? Yes, 50k multiplied by? Right, but what did we say last time was log e? 1. So this is 1. So the equation is then natural log 12 over 3.2 equals 50k. So then you will give me an equation for k, and I will be ready to plug it in the calculator because I can't do this by hand. How do I solve for k? Both sides by? Indeed. So let's punch it in the calculator. No one can do this by hand. So the top is natural log, and it's 12 divided by 3.2, close the parenthesis, and I divide everything by 50. Here it is, 0.0264. So k equals 0.0264. What does this mean? Can anyone explain? And then I'll put it in the model. It means that the population growth rate is 2.64%. So 2.64%. So now I have A of t, which is 3.2 times e to 0.0264 t. And I have the entire model. I was really asked to determine the original, the initial population, and the growth rate. So the population of Palestinians in the territories the population grows at 2.64% per year. Question part B. In which year will the Palestinian population be 9 million? Please tell me what I have to write in order to determine when will the population be 9 million. Exactly, thank you. 9 million equals 3.2 e to 0.0264 t, assuming the model still holds. Okay, the same thing from before. What is the very first step? Clean it up, yes. I have to divide by 3.2. So 9 divided by 3.2 equals e to 0.0264 t. Now I'm ready to bring that power down, otherwise I will never be able to solve it. So how do I bring that power down? Yes, so natural log of 9 over 3.2 must equal 0.0264 t times natural log e, which is 1. So then t equals natural log 9 over 3.2, 0.0264. Punch it in the calculator. So natural log 9 divided by 3.2. So I will just copy this. So it's 9 instead of 12. You don't have to do this. Oh, never mind. I messed it up anyway. So natural log 9 divided by 3.2. And everything divided by 0.0264. And enter. So 39, approximately t is approximately 39 years, which means if the model continues in 2039, the Palestinian population will get to 9 million. Any questions on this? Is it pretty straightforward or not? It's the first time you saw that, correct. Okay, I would like to talk about the exponential decay. So let's look at a problem. Okay, they all have, all these problems that I'm looking at right now, they all have half-life. So let's talk about half-life. I thought I could find a problem before we talk about half-life. Okay. Let's say the half-life of a radioactive substance is 2 years. What does half-life is? Let's say we have 100 milligrams of this substance. What will happen 2 years later? We have 50. It gets halved, right. What happens 2 more years later, or a total of 4 years later? 25. And so on and so forth. Agreed? Okay. Now, if I say we start with a mass of 100 milligrams, and we have the half-life 2 years. And let's say I'm asking you now, find M of 30 years. That's a question. I have 100 milligrams. I know the half-life is 2 years. And I'm asked to find what happens, how much is left in 30 years from now. Okay? Here's my first step. I will write the model. And I know that the model looks like this. The mass at time t equals the initial mass times e to negative kt. Two things I don't have, sort of. I need to find, right? I need to find the initial mass, which I have. You're right. But what I don't have is the decay rate. So if I have this and I have this, I can punch in 30 and I'm done. But I don't have this. But I know that in 2 years, every 2 years, so for now I have the m of t equals 100 times e to negative kt. So the only unknown is the radioactive decay rate. Once I find that, I can punch in any t I want, including 30 years. Would you agree? Okay. So if I start, so this tells me that when t is 2 years, then m of 2 years will be 50. I want to put this information in the model, exactly how we just did a few minutes ago. So can anyone tell us what is this? In 2 years, this is 50 equals 100 times e to which power? Right, 2 with negative and k. Very good. Negative 2k. Like before, what do you think we're going to do first? No, I cannot apply natural log till I clean it up. It's not cleaned up yet. Divide by 100. 50 divided by 100 is 1/2. Now, yes, I have to apply natural log to both sides. So let's apply natural log to both sides. So then natural log of 1/2 equals, what is left on the right-hand side? Very good, negative 2k. So then k must equal natural log 1/2 over negative 2. Perfect. Good. So I go back to the calculator. I punch in natural log in parentheses of 0.5, which is 1/2, and I divide in parentheses by negative 2. And when I click enter, I get 0.3466. So k equals 0.3466. I go back and I put it in the model. So m of t equals 100 e to negative 0.3466 t. And now I'm asking you, can you tell us how much is left in 30 years? We have the model. No secret whatsoever. What will you determine? M of 30. So go back to the calculator. So I have 100 times e raised to, I like to put parentheses, negative 0.3466, or I can recall this number, that's even better, multiply by 30 and close the parenthesis, and I will have left in 30 years 0.003 milligrams. 0.003 milligrams. It's what is left in 30 years. Okay, we have time. I think we should at least start another problem. Let's look at problem 19. If I promise to stop in 5 minutes, if we finish it or not. So, prehistoric cave paintings were discovered in a cave in France. The paint contained 15% of the original. Mass of carbon-14. Estimate the age of the paintings. This sounds terribly difficult. One more time. Prehistoric cave paintings were discovered in a cave in France. The paint contained 15% of the original carbon-14. Estimate the age of the paintings. Okay. Oops. Okay. So I know we're talking about radioactive decay. And I know what I have to write. What is the model that I have to write? Can anyone dictate? M of t equals m0. It's the e to negative kt. Perfect. Do I have the original? No. But what do I know right now? This is 15% of the original. How do I write 15% of the original? Say it again. 0.15 of the original. What is the original? How do we call the original? No, not T.
K.
Not K. Which one? Which is the original? What is the notation for the original? Exactly. So today, this is 15% of M0. What do you want me to write? What would you tell me to write? 0.15 m0 equals m0 e to negative kt. I think I did not read the top of the problem. Let me read the whole thing. I only read partial.
Oh, it gave you K.
That's what.
Yeah, it's negative 0.00012 T. So
Okay, K. Okay, I didn't copy it. So K equals 0.000121. The negative is in the model. So K is, yes, I didn't copy that. Because I realized all of a sudden I had two variables. I said, oh, good. So what do you think? So of course I'm going to replace K by this. So the equation is 0.15 m0 equals m0 e to negative 0.1230121 t. Okay, so look at this and say, oh, I know what you're going to do first. And I'm pretty sure that's exactly what I have to do. What will you tell me to do first? And we did that in all equations.
Go back.
Exactly, of course. I have to get rid of that. Absolutely. And then from here is straightforward. 0.15 equals e to negative 0.000121 t. And then natural log. So then I have natural log of 0.15 equals negative 0.000121 t. And therefore t equals natural log of 0.15 negative 0.00121. So natural log 0.15, everything divided by, in parentheses, negative 0.30121, close the parenthesis. Okay, 15,678 years. T, 15,678 years.